All right, good afternoon, everyone. Hope your day is going well so far. So today we'll be talking about two special cases of matrices. The first, which you see in the aim, is called an inconsistent system, and the second is a dependent system. So an inconsistent system is going to be one that has no solutions, and a dependent system is one that has infinitely many solutions. Okay, so inconsistent is no solutions, dependent is infinitely many solutions. All right, but to start us off, for you now, it's to use Gaussian elimination to solve this system. And it actually be one of the two here. So it's either going to be inconsistent or dependent. Okay. All right, so take another 30 seconds to work on that, and then we will discuss.
Dependent is infinite many solutions, right?
Yeah, so dependent is infinitely many, and inconsistent is no solutions. Okay, so Ryan says it's inconsistent. Let's take a look. So I'm going to scroll up for the solution, unless someone still needs the slide here. Well, actually, let me mention the homework is extra credit because of spring break. Okay, so this is due the Monday we come back, and it's extra credit. Okay. All right. So let me go to the solution. All right, here it is. Okay, so we have this system here, which I'm going to write as the matrix, right? 1, -8, 4, 11, 2, -12, 12, 17, and 1, -4, 8, 22. Okay, so it'll be R2 minus 2R1. Because again, Gaussian elimination, we want zeros under the 1 in the first column. Okay, so I want a 0 here in place of the 2. So -2R1 is going to be -2, 16, -8, -22. And I'm going to add that to R2. Okay, so 2 minus 2 is 0, -12 plus 16 is 4, and then 12 minus 8 is 4, and 17 minus 22 is -5. Okay. Actually, one thing, yeah, I'm trying to figure out where to place these row calculations. Normally in class, on the board, I write it under the new matrix, but on paper, it might be actually better to write it under the original matrix. Let me know if you have any thoughts on that, but this is what put that here. Okay, so these line, and then you can add row 2 and -2R1 to get, 0, 4, 4, -5. Okay, so we have the 0 here. Next, we want a 0 also over here. So I'm going to do row 3 minus row 1. Okay, so 1 minus 1 is 0. Then -4 minus -8, that's -4 plus 8, so that'll be 4. 8 minus 4 is 4. And then 22 minus 11 is 11. Okay, so we have that there. All right, so we're done with the first column. Next, we move on to the second column. Okay, so I'm going to do row 3 minus row 2. And technically, you can also, at this point, you can also divide the second row by 1/4, or sorry, divide it by 4, or multiply by 1/4, because that will give you a 1 here. I choose not to do that though, because, if you do, 4 minus 4, you get 0, which is what we want. Okay, so row 3 minus row 2, you get 0, 0, 0, and then 11 minus -5 is 16. Okay, so that's the last row. Okay, at this point, technically this is not in, it's not in row echelon form yet because we don't have the 1 here, but we can, write it as a system of equations. And we'll see that, as Ryan said, right, this has no solutions, right, because the last equation is actually a false equation, right? Like you have 0 equals 16. This could also represent 0z if you want, right, I'll just write 0 equals 16. I think that's clear to make my point. So 0 equals 16, which is a false equation, which will never be true, right? Which means that this system of equations has no solution. Okay. All right, so that's the answer. This system has no solution, and the word we use for that in the context of matrices is inconsistent. All right, does anyone still need to copy this solution right here? For the Arduino, you can type in the chat or speak up. Okay, not that I'll move on. All right, so let me give you an overview of the rest of the lesson. So we're first going to define inconsistent, which, the matrix in the Arduino was inconsistent. And then we're going to talk about the other case from the AIM, which is a dependent system, and that has infinitely many solutions. Okay, and then find that, and then we're going to close with something called the complete solution to a dependent system. So you're going to see that even though a dependent system has infinitely many solutions, there's actually a way we can describe the pattern. So even though there's infinitely many, it still follows a certain form. But you'll see what I mean when we get there. For now, though, let me scroll down to the solution of inconsistent. All right, can I get a volunteer to read this definition for us, please?
All right, I can read. Okay. Definition: a system with no solutions is said to be inconsistent. No, a system has no solution if we end up with a false equation after applying Gaussian elimination.
All right, thank you for that. So yeah, the do now was an example of that. And if you end up with a false equation, as we did in the do now, right, the last equation was like, I think it was like 0 equals 16 or something. But yeah, if like you have 0 equals something else, right, that's a false equation. That will never be true. So that means that that system would have no solutions. Okay, so make sure you have this in your notes, and then we'll move on to the second half, which is the second case of dependent systems. All right, is anyone still copying the definition here? All right, now I'll move on. All right, next we'll talk about an example of a dependent system. Okay, so again, dependent means that, and I'll define it later, but dependent means that there's infinitely many. Okay, so here's this system here, negative 5x minus 10y plus 75z equals 10, etc. And at this point, you can actually, it'd actually be better to divide this by 5 first, or negative 5, and then write it as a matrix. But you'll see that I do that in the first step. That actually be quicker if you divide first and then write it as a matrix rather than add and write 2. Okay. All right, anyways, these are the coefficients of the system. And then I do -1/5 R1. That's 1, 2, -15, -2. And then I do, so again, we want to use Gaussian elimination to get zeros in the first column below the first one. Right, so I'm going to do R2 plus R1. And that's going to give you 1 plus -1 is 0. Then 2 plus 0 is 2. -15 plus 7 is -8. And then -2 plus 4 is 2. Okay, and then row 3 was the same. And then I do R3 minus R1, so that'll be 1 minus 1 is 0, 1 minus 2 is -1, -11 minus -15, so careful with the negative signs, that's going to be +4, -3 minus -2, that's going to be -1, which is what we have here. All right, so we have the zeros in the first column. Next, we'll move on to the second column. Okay, so I'm going to do, at this point, you can also do like 1/2 R2 first and then add, but I decided to do R3 plus 1/2 R2 in this case. Either way is fine. 1/2 R2 is going to be 0, 1, -4, and 1. Okay, I'm going to add that to row 3. Okay, so 0 plus 0 is 0, -1 plus 1 is 0, 4 plus -4 is 0, and then -1 plus 1 is 0 also. Okay, and then lastly, I did 1/2 R2 to get it in row echelon form. Okay, so you have the staircase pattern and then and the ones as leading entries, and then any row, right? This is the example that we didn't like see in the past few days, but like this was the last condition in row echelon form. Any row with all zeros has to be in the bottom. Okay, so that's the third condition that's met, and then I'm gonna write it as a system now. So x plus 2y minus 15z is -2, y minus 4z is 1, and then 0 equals 0. Okay. And this equation is always true, right? No matter what number you plug in for x, y, z. So, I mean, technically this could represent this, right? Whoops. Plus 0y plus 0z, right? For any x, y, z that you plug in, right, you could do like 1, 1, 1 or 1, whatever, right? Doesn't matter what x, y, z is, this is always true. Actually, it might be more helpful if I represent it like that. Okay. But yeah, there's infinitely many solutions for this system. Okay. All right. But yeah, next I'll define what a dependent system is, and then we'll close with one more question. All right. For now, let's just make sure you have this in your notes, and then we'll move on. All right. Does anyone still need to copy this? All right. If not, then I'll move on. Okay, so this is the definition of dependent. I'll actually scroll down to the slide. So on the slide, I actually only include the first definition without the note. Reason for that is I didn't want to like overcomplicate it, and at least in this class, we're not going to see like examples beyond like the 0 equals 0 case in the bottom row, right? So yeah, I just have that just one sentence for the definition. But that being said, there are other cases in which it's dependent without like the zeros at the bottom. Okay. But I can show you that later if you want to see that. All right, for this definition, I saw a SLU earlier. Can you read this one here?
Definition: a system with infinitely many solutions is called dependent.
Oh, okay. All right. Sorry, I think Salu signed off. All right. I think he's having connection issues. Anyways, um, yeah. Thank you for that, Ryan. A system with infinitely many solutions is dependent. Okay. That's just the wording for it. You'll see that in the homework for this lesson. Okay. So yeah, if they ask you to find the complete solution to a dependent system, this is what it means. All right. I'm going to move on to the next and last problem, okay, assuming that everyone copied this already. All right. So, as I mentioned earlier, right, there's something called a complete solution to a dependent system. So, again, even though there's infinitely many solutions, all right, there's still a pattern to those solutions, as we'll see in this example. Okay, so this question says find the complete solution to the dependent system from the previous question, right? So this is like the matrix in the last step right here, right? Same matrix. Okay, so but now we're going to find the complete solution. And I'll explain what that means, complete solution, in this problem. Okay, so first I'm going to convert it to a system, right? So you have x plus 2y minus 15z is negative 2, y minus 4z is 1, and 0 equals 0. All right, first thing we're going to do is let z be a parameter. Commonly we use the letter t. And you might be thinking like you can just let z equal z, right? And you can actually do that, but the reason we choose a different letter outside of x, y, z is because we want to emphasize the point that this parameter is outside the system, right? So it's just like an independent variable that we use to describe the set of solutions. So that's why we don't normally use z. Okay, we use the letter t usually, like, and you know, you might see that in physics actually, like t equals time, so that'll be like the parameter, and then you can describe the other equations like this. All right. Anyways, we're gonna let z equal t, where t is any real number, and after that you just solve as you would normally. So y minus 4z equals 1, right? But in this case z equals t, so we get y minus 4t is 1. And then we're going to add 4t to both sides. We get this, y equals 4t plus 1. And for x, we get x plus 2y. And as we solve here, y is equal to 4t plus 1. So we have that here, minus 15z. And again, z is equal to t, so we have that here, equals negative 2. And then we solve. So we have x plus 8t plus 2 equals negative 15. Sorry, x plus 8t plus 2 minus 15t equals negative 2. And then we're going to get x minus 7t. And then I subtracted 2 from both sides, get negative 4 on that side. And then I'm going to add 7t to both sides, and you get x equals 7t minus 4. So the solution is 7t minus 4, 4t plus 1 for y, and then t, z equals t, where t is any real number. And so this is the complete solution to this dependent system. Okay, so what I was saying earlier about, having infinitely many solutions but having a pattern, this is what I mean. Okay, so even though there are infinitely many solutions, they have to follow this, these three equations, right? So you can let t equal be any number. Like for example, like if you let t equal 1, then t equals 1 here, that's the z coordinate, and then y would be 4 times 1 plus 1, that would be 5, right? And then for x, it would be 7 times 1 minus 4, which is 3. Okay, so that's like follow that form. And then if you let t equal 2, you would have 2 for the z coordinate, and then 9 for the y coordinate, and then 14 minus 4, so that would be 10, right? Yeah, so there are infinitely many solutions, but they have to, still meet these 3 equations, right? This is how you would describe that solution. Okay, so with that being said, while you finish copying this, let me close with announcements. For one, there is SGI today, per usual, 2:47. Drop out if you have questions. Secondly, a reminder that the homework for this lesson is extra credit because of the break. Okay, so that's due on the Monday we come back. Third, reminder that there is homework due tonight, so that will be homework 82. So please submit that by midnight tonight. And then lastly, the next quiz, I think it's quiz 8, that's going to be the Friday we come back from break. Okay, so quiz 8 is the Friday we come back from break. I know I haven't gotten around to finishing grading quiz 7 yet, but I'll do that definitely over the break. Okay. All right. Oh, and yeah, I'll send the topics list over the break as well. The topics list for quiz 8, the upcoming quiz. All right. Yeah, that's all I have to say for today. If you're done copying this and you don't have questions, you're free to go, and I'll see you in about 10 days. All right, take care.
Have a nice day.
Enjoy
Thank you.
your
Have a good day.
Enjoy
All right,
your
thank you too. Hey.
Have a great break, Mr.
Oh, all right, thank you too.